Hello friends, very good morning. In today's session, we are going to derive another important derivation on the keys. Friends, the question for today's session runs like this. So he says, prove that a square key is equally strong in shear and compression or crushing. So what's the meaning of this? First of all, we should know what a square key is. Friends, by definition, a square key is a machine element having a square cross section. That is, it will have B and height h. Width is B, height h, and the length of the key will be L. And here, since it is a square key, B is equal to h. So we should remember this concept very well. He says, prove that this square key which is equally strong in shear and compression. That is to say, if you are using a square key for transmission of power, prove that the torque transmitted by the key in shear and that in crushing or compression are the same. That is, if you know what is the torque transmitted by the key in shear and that in compression, you have to prove that these two quantities are the same or the ratio of these two is equal to 1. Friends, in the previous session, that is in derivation 1, we have derived what is the torque transmitted by the key in shear in general, that in compression also we have done. So let us write down what is the torque transmitted by the key in shear and that in compression. So we can have, friends, here we have done in first derivation empty key in shear is equal to that already BL tau K d by 2 is equation number 1. Here we have B is the width of the key, L is the length of the key, tau K is the shear stress for the key, and d by 2 is the radius of the shaft. Similarly, friends, we have derived the other expression empty key in crushing or in compression, both are same, is equal to h by 2 into L into sigma c into d by 2. We'll call this as expression 2. But remember, friends, in the examination, if this derivation is asked, you have to derive these two first and then equate them or find out the ratio of these. Friends, now we have the expression for the torque transmitted in shear and also that in compression. We will find out the ratio of these two. So now I will just find out the ratio of these two, the torque transmitted in shear and that in compression. So empty shear, that is the key, divided by empty of the key in compression or crushing. So we know the expressions. So we will divide one by the other. So this is B L tau K d by 2. And this expression for the crushing, it is h by 2 into L into sigma c into d by 2. Friends, you can just cancel similar terms and simplify this expression. D by 2 gets cancelled, both the numerator and denominator. L gets cancelled and you are left with this B goes to the numerator. You will have 2B tau K divided by h times sigma c. A very simple derivation. Friends, for a square key, you know, the width of the key is equal to thickness of the key. So we can cancel B and H also. And this gets reduced to 2 times tau K divided by sigma c. So the ratio of these two is equal to 2 times tau K divided by sigma c. Friends, generally for the engineering materials such as sharp keys or say steel, etc., the compressive stress of the material will be double the shear stress. That is, sigma c is equal to 2 times tau K in general cases. So using that information, we can cancel 2 tau k equal to sigma c, and this becomes equal to 1. That is to say, friends, the empty key in shear to empty key in compression is equal to 1. And if you cross multiply, you will have empty key in shear is equal to empty key in compression. That is, we can write down this as empty key in shear is equal to empty key in compression in crushing or compression. So that is to say, a square key which has got width b, thickness h, where b is equal to h. The torque transmitted by the key in shear is equal to torque transmitted by the key in crushing. Or in other words, we can generalize that a square key is equally strong in shear and compression. Thank you, friends.